All right, so I want to do an example on confidence intervals for Gaussian distributions. Okay? So the idea is that if you have a distribution, right, and this is, I'm going to say this is z, okay, and this is at 0, I want to know the probability, well, I want to know the probability that everything falls within here with a certain confidence interval of 1 minus alpha, okay? And the area here and here is alpha over 2, okay? This notation is kind of weird, but basically it looks like this, okay? Let's say you have a batch of resistors, okay? And the mean of those resistors is 25 ohms, and the standard deviation is 0.5 ohms, okay? I want to know the range on mu, right? So if I change this to x and I put 25 here, I want to know what this variable is. I want to know this range where 90% of my resistors are going to fall into that band, okay? And so the way you write this is you say, this is actually x bar, because they actually told you that you only sampled 36, resistors, and this is actually S, where S is the sample standard deviation. Now it turns out there is an interesting property that as long as you have more than, and I forget, let's see, yes, as long as n is greater than 30, you can use a z distribution. If you have less than n, if you have less than 30 samples, your distribution is not completely Gaussian or statistically Gaussian, and you have to use something called a t-star distribution. That's a completely different, well, it's not completely different, but it's a different table and it's a different kind of thing. All the problems that I'm going to assign at least, and what I'm going to go over right here, are only in the z distribution. And so in this case, you have 36 samples, so you can use the z table. And so basically what it says is, if my mu, right, this is the sample mean, what is the mean of, like if I only took 36 samples, imagine I took 3,000 samples, right? The mean would probably not be 25, it would probably be something different. But give me your 90% confidence that the mean will fall in between two numbers. And what are those two numbers there? This number over here is going to be your sample mean plus z alpha over 2, and I'll explain that in a minute, times s over square root of n, okay? X bar is this here, this is x bar, and this number here is x bar plus z alpha over 2, s over root n, okay? This number over here then obviously is just going to be minus, so x bar minus z alpha over 2, s root n, okay? So what is this z alpha over 2? Well, I told you in a previous video that the z distribution has a particular distribution that's always constant. The mean is 0 and the standard deviation is sigma. And so if you do a change of variables and change your entire system into the z domain, then you can go into the table and figure out what these numbers are, okay? So the idea is that this here is centered at 0 and it's moved, or its standard deviation is 1. And so if you plot the z distribution with a mean of 0, I want to find this number here, where this is alpha over 2, this is alpha over 2, and then this in here is 1 minus alpha. Because if I find this number, right, this is the z-axis. If I find this number, I know that the area under this curve is 90%. And then what I'm going to do is I'm going to translate it by multiplying by this, s over square root n. I'm going to translate it using this to get it to my 90% confidence. Okay? Now what this means is that alpha in this case, so 1 minus alpha is 90%, right? Because I want my 90% confidence. That means that alpha is 10%, okay? And it means alpha over 2 is 5%. So that means I need this percentage to be 5%, and I need this percentage to be 5%, okay? If this area in here is 90% and symmetric on both sides, then that means that this whole area here is 50%, and this whole area here is also 50%. If this whole area here is 50%, 50 minus 5%, that means this area in here is 45%, okay? So if I want to find z alpha over 2, I need to go back to this table, okay? And I need to find where z hits the area. This table tells you the area under the curve. So I need to find 0.45. And I'm not going to find it exactly. I found 0.4495. So z alpha over 2 equals 1.64. The area under the curve is 0.4495. Z alpha over 2 equals 1.65. A of z equals 0.405, 0.4505. So the z alpha over 2 that I'm looking for is in between here and here. So I'm just going to say, you know what? Pick 1.645. That's my z alpha over 2. Okay? The book says they got the same thing I did. Okay? So then at that point, can you see me if I sit down? I'm kind of tired. The book basically says, okay, take your 90% confidence on mu is x bar, so that's 25, plus or minus z alpha over 2, so 1.645, times s, your sample deviation, 0.5, over square root of 36. And what they get is that their range on mu is 25.14 ohms, make sure to put units, and 24.86. And so what that means is that they took 36 samples, they are saying they have a 90% confidence that the true mean of the entire distribution of resistors in the entire universe, or for this class of resistors, is going to fall in between these two numbers here, okay? And that is how you use the z-table in your textbook, and I'm going to assign some homework problems on that. At this point, this concludes the distribution section of statistics. And so next week, we are going to move on to trend line fitting and do a week of trend line fitting. So I hope you enjoyed this bit on distributions, and I'll see you next week.